So today we're going to do something which is a bad idea. Bad idea. I'm just going to write that down. Okay? This is not actually a technique you should do, but it is something that I think that if you go, what? And try to figure it out, you learn a lot. So sometimes a bad technique is extremely illuminating. It's not something you actually want to do, but whatever. So let's say we're doing 656 divided by 12. All right. So you can cancel common factors. You can do long division. You can do whatever. All right. I am going to do polynomial synthetic division on this. So the idea here, and it's an interesting idea. It's not actually efficient or effective or anything, but it's a pretty cool idea. Think of the polynomial as 6x squared plus 5x plus 6. Notice that when you plug in p of 10, you get 600, because 10 squared is 100, plus 50 plus 6 equals 656, right? I am using the representation of the numbers in base 10, basically. That's so 10 squared, 10, 10 to the 0, 1. In the setup, our divisor, we'll call that d of x, will be x plus 2. And of course, d of 10 would be 10 plus 2, or 12, right? So our goal is p of x to be equal to d of x times q of x plus r of x. And more or less, if I plug in 10, I hope that q of 10 gives me the division by 12. And r of x would give me the remainder. It kind of almost does that, but not quite, but we'll see. Again, this is a particular example that works out reasonably well. Other examples wouldn't. And because I want to do synthetic division, the leading number here, or the divisor, has to be 1. If it isn't, you could probably do something, but it's not worth the trouble or effort. This is just to illustrate a different way of thinking. All right, so synthetic division. So I'm dividing by x plus 2, so I put a minus 2 there as that number, 6, 5, 6. And I just do 6 times minus 2 is minus 12, which is minus 7, times minus 2 is 14, 20, right? And so q of x, the quotient, is 6x minus 7, and the remainder is 20. All right, so now let's look at p of 10, or d of 10 times q of 10 plus r of 10. All right, so what 656 was. D of 10 is equal to 12, and then times q of 10. 60 minus 7 is 53, and then remainder of 10 is, is 20. So the fact that 20 is greater than 12, it's a slight problem. Remainders are supposed to be less than the divisor. So if I write 20 as, and this is where the method kind of like, because that remainder could be any size. It's not really constrained, and you need it to, whatever. Anyway, so it's 12 and 8, and so this is 12 times 54 plus 8. And now that is my answer to the division, because when I divide by 12, I get 54 and 8/12. Again, there's some common factors I could have divided by. This is 54 and 2/3. But in any event, so that's 656 divided by 12. So weird, right? So the synthetic division is actually kind of pleasant. And just to contrast, 12 into 656, right? That's more or less 5 times 12 is 60, and you got 56. 12 into 56, 4-ish, 48, 8, so 8/12. Right, so long division isn't so bad, but I'm thinking about it, right? Synthetic division I didn't think about at all. It's just totally automatic. So it's a real bummer that it doesn't actually work out terribly well, because I still have to do some work at the end. And it could be a lot of work. This remainder could be way, way off. So you can also extend this bad idea to a divisor with multiple digits, again with the leading 1 in front. And then you just use the longer form of the synthetic division, so it gets a little bit more complicated, and it'll probably be even worse performing. But anyway, I think my motivation for doing this is hopefully to throw in, like, what the heck is going on here, right? It's not to be like, oh, these are the rules for doing this. No, it's a bad idea. Don't do that, right? Don't do division with this. But do try to understand what's actually going on. The representation, right? Representing a number with this polynomial, with plugging in x equals 10, and you get the base 10 representation of the number. Factoring the polynomial, dividing that polynomial and getting a remainder, and boom, good to go. You could, of course, do long polynomial division for divisors that don't start with 1, but again, bad idea. So you get that, understanding that p of x is, this d of x times q of x plus r of x, that's the form we're trying to get into. And then when you plug in 10, you have some decomposition using the divisor, but it hasn't fully necessarily reduced. You can even have negative remainders or whatever, but still, it's a neat little gimmick.